Okay, so we are now starting on the counterpart to derivatives, the integral. And the big intuition to keep in our mind here is that the same way that intuitively we would think about the derivative as the slope of a function, we're going to think about the integral as the area of a function, or the area under a curve, giving us that. So first let's start with this, just to get the basic notation out of the way. So for certain functions, f, on some closed interval to r, that we call integrable, we will define a number called the integral of f on the closed bound, ab, and denoted by this weird symbol. The integral from a to b of f is typically how we read that. So it's just a number that we're going to assign to certain types of functions that look like this. The intuition for what this number will capture is the area under the curve on that interval. So if I've got some function, who knows what it is, defined on some closed interval, ab, my integral is going to give me the area under the curve on this interval ab, that shaded in area. That's ultimately what it's going to give me. Now, the same way that when we started talking about derivative, we said, look, if I told you to naively try and figure out what the slope is at a point, what would you do? You would have picked one point, you would have picked the point that we're trying to calculate the slope at, picked a point a little bit to the right and calculated the slope using those 2 points, and tried to get the slope that way. And then we took the limit of what you're doing there, and we said that's what we'll define to be the derivative. Very similar thinking going on here. If I gave you this, and I said try to figure out what the area is, assuming you knew the function, so you can figure out the height of all these points at any point you wanted. And if I told you to give me what's the area of this curve, you might do something like this, right? You don't know how to calculate the area of this, but if you made a bunch of little rectangles here, you know how to calculate the area of each of those rectangles, right? So you might have drawn some lines and said, okay, so I'll take this and I'll divide it into a bunch of small pieces, whatever, doesn't matter how many. And then I'll make a rectangle here, and I'll make my rectangle so I never actually get over the line. So once my rectangle touches a point on my function, I'll just draw the top there. And now you could figure out what the height of this rectangle is, right? It's just a value of the function at this point. The height of this rectangle, you can find the heights of all these rectangles. You can calculate the width of each of those rectangles, and you know how to find the area of the rectangle. Length times width. You add up all those areas, and that would give you a good approximation for the area under this curve, right? So, where we're going to be going with this is, okay, what happens if we split this into infinitely small pieces? And you do that exact same thing. And that's ultimately where how we're going to calculate our integrals. Does that make intuitive sense where we're headed? That's what this whole chapter is about. Chapter 5. Okay, so this is where we're headed. Let's go back and let's get some very basic definitions. So in calculating the area, the first thing I had to do was divide this interval AB up into a bunch of smaller pieces, right? That's the first thing you did. You divide this up into a bunch of small pieces, and then you calculate the rectangles. So the first thing we're going to talk about is dividing the interval AB up into a bunch of small pieces. Here's what we're going to say, and then we'll read the definition over there. So if I've got some closed interval, A, B, I'm going to divide it up into n pieces. So I'm just going to divide this up into n pieces. I'll pick n to be 3. Doesn't matter. There we go. I just split it up into 3 pieces, right? They're different sizes. Doesn't matter. I just arbitrarily chose 3. Here's what we're going to do. I'm going to call this point here where we start our interval, x0. And then I'm going to call this point x1, this point x2, and then this point x sub n, or in our case x3. However many intervals I divide this thing up into. The set x0, x1, x2, x3, we're going to call a partition. That's all a partition is. This is a partition on AB. What do we mean? We mean it divided AB up into a bunch of different parts. And we're going to call each one of these a partition interval. So here's one partition interval, x0 to x1. Here's another partition interval, x1 to x2. And then here's our last partition interval, x2 to x3. Notice, if I divide AB up into 3 parts, I need 4 points to do that. So I divide it up into these 3 partition intervals. I have to use 4 points to do it. So as we're going through this, you're going to see a lot of the times where I is greater than or equal to 1. Well, I'll make reference to that when it comes up. But just note, we always have one more point than we have partition intervals. Makes intuitive sense, right? All right, so let's go back to this definition and wrap our heads around it. So let A equal x0, B equal xn, and we have x0, and we have x1, x2, in between them. So A is equal to x0 is less than x1 is less than x2, all the way up to xn is equal to b. Then we call P equal to all those x's a partition of the closed interval AB. We call each of those little x sub i's a partition point of P, and we call the interval x sub I minus 1 to x sub I, these things, a partition interval of P. Notice that these are only defined for I greater than or equal to 1 and less than n. You can't plug 0 into that, because then we get x sub negative 1 to x sub 0. That doesn't make sense. Our first one is x sub 0 to x sub 1. So the same way that this is only defined for 1 less than or equal to I less than or equal to n, in our case 3, same way these are only defined for I less than or I greater than or equal to 1 and less than or equal to n. That's why there's that restriction, because there's one more partition point. Okay. So any questions so far on what a partition is or what a partition interval is? Pretty straightforward? All right. So next, if f is a function on AB, if f from AB to R is bounded, and if P is a partition on AB, then for each I greater than or equal to 1, that means we're going to be talking about partition intervals, we define m sub little I to be the smallest point reached on that interval, and we call big M sub I to be the largest point reached on that interval. The greatest lower bound and the least upper bound. So what we're saying is, I now have, so here's some interval. That point's A, that point's B. And imagine that I have a function defined on this interval. What does the function look like? Doesn't matter. There it is. Pick one of our partition intervals. Doesn't matter which one you pick. We'll pick this one. So look at the function defined on this partition interval. So x sub 1 to x sub 2 is our x sub I minus 1 to x sub I. Now we're saying m sub little I is the infimum. It's the greatest lower bound of the function on that interval. So on this interval, what's the greatest lower bound? Probably this point right here. So this is m sub I. The height of that point is little m sub I. And then here, we say big M sub I is a supremum of the function on that interval. It's the least upper bound. The least upper bound, the smallest point that's greater than every other point on the interval, which is this point right here. That's M sub I, big M sub I. In this case, we were talking about in the first interval. Oh, second interval. This is the first, this is the second. So this is little m sub 2 and big M sub 2. And we can do this for every interval. We can do it for the first interval, for the second interval, for the third interval, etc. Depending on how many intervals we have. That's all this is saying. Oh, I had a picture here. So, same exact picture. We have some partition. Eventually we get to this part, this partition interval, from x sub I minus 1 to x sub I, whatever those numbers are, just somewhere along the way. M sub little I is the smallest point the function has on that interval, and M sub big I is the biggest value the function has on that interval. Pretty straightforward? Okay, wonderful. So we're going to be referencing these little m sub i's and big M sub i's from here on out. They always mean this exact thing. We're not going to reference this definition over and over again. It's just going to be assumed you know what I'm saying now. Okay. So now we're ready for our first, well, not our first, but our next definition. And that is the lower and upper Darboux sum. We're named simple concepts. This is the lower Darboux sum of the function f with some given partition P. What is the lower Darboux sum? It's the sum you get when you make your areas. It's the exact same thing we did right here. We're adding up little m sub I times the distance of every interval. Take some interval and multiply it by the smallest height it achieves on that. Take the next interval, multiply it by the smallest height it achieves on that. And again, and add those up. It's doing exactly what we did right here. It's calculating the area of these rectangles. Notice that this height right here would be m sub 1. This would be little m sub 2. This would be little m sub 3, etc. This would be little m sub n. And notice that the distance from this point to this point is this point minus this point. If this point happens to be at 10 and this point happens to be at 8, what's the base of my rectangle? 2. 10 minus 8. That's exactly what this is saying. Take your right-hand point minus the left-hand point. That gives you the base of this one little triangle. And multiply it by the height. Base times height. Add it up for all n. I said triangles. I meant rectangles. And there you go. That's your lower Darboux sum. It's the sum you get when you make your rectangles, you always use the lowest point. Now there's nothing magical about the lowest point. We could have also done it using the highest point, right? So I could have made this rectangle right here come up all the way to there. I could have made this one come up all the way to there. This one come up all the way to there. This one come up all the way to there. This one comes up all the way to there. This one comes up all the way to there. This one all the way to there. And I could have done my rectangles that way, using the highest point now on each interval rather than the lowest. And that's exactly what the upper Darboux sum is. So lower Darboux sum, it's calculating the area using all the rectangles that barely reach the line. Upper Darboux sum, it's using all the rectangles that barely go over the line. Make sense? Now something better be screaming out to your intuition right now, that whatever our real area is, it's somewhere in between the lower and upper Darboux sum. So we've now sandwiched our real area between some upper sum and some lower sum. Does that make sense? Wonderful. And then I also had a picture in case you need a more dramatic example. So very, very simple case. We're going to look at a function defined on an interval where we only use a partition of 3 points. Here's your lower Darboux sum rectangles. Here's your upper Darboux sum rectangles. In a very simple case where it's very dramatic to see the difference between what they give you. Okay. Now notice that little m sub I, by definition, is always going to be less than or equal to big M sub I. Little m sub I is the smallest value a function reaches on some point, on some interval. Big M sub I is the highest point the function reaches on some interval. These were meant to be the same function twice. I don't know if that's clear. Same function, same partition. In one case we use little m sub I. In the other case we use big M sub I. So since little m sub I is the least, or is the greatest lower bound, then it's always a lower bound. Since big M sub I is the least upper bound, then it's always an upper bound. So by definition, this is always greater than or equal to this. And hopefully that makes intuitive sense as well from here, but also makes perfect sense just based off of their definition, obviously. So, since little m sub I is always less than or equal to big M sub I, then our lower sum is always less than or equal to our upper sum. Question, when would those ever be equal?
A constant function.
A constant function, perfect. So my function is just a constant function like this, and we have it on this interval. Then when we divide this up into rectangles, doesn't matter how we divide it up, the lower and upper sums are going to be the exact same thing, which in that case is going to happen to give us the actual area. So just corner case to make sure you understand what we're saying. Okay, and then intuition. We already said this, but we'll say it again. Intuitively, you should be thinking in your head, whatever the real area is, it's somewhere between the lower Darboux sum and the upper Darboux sum. Right? Okay.
So, I'm trying to see where we're going with this, and then as we progress in the chapter, is it going to turn into taking...
Take the limit of that and the limit of that, and if they're equal, you got your area.
Take the limit of the sum?
The limit of these Darboux sums, when we make our partition, get smaller and smaller and smaller intervals, or the biggest distance in our partition gets infinitely small.
So it's kind of like you have an infinite partition, and then you get infinite sum of that partition.
A special type of infinite partition. An infinite partition where our points get arbitrarily close. Because if I did a partition like this, so we got some function, and it's defined like this, and I start by, we'll say it's defined from here to here, and I start by, okay, my first partition point, I may divide this in half, and then I may divide this in half, and then I may divide this in half, and then this in half, and then this in half, and da-da-da-da-da, put infinitely many points in there. This is still a horrid approximation, and it's not going to give us the area. So yes, a special type of partition. A partition where the distance between our points goes to 0. But yeah, I think you've got the big idea where we're going. Okay. Very useful sum that we're going to be doing over and over again. What is this sum? If I know that P is a partition on the closed interval AB, what is the sum of all its partition interval distances?
P.
Not P. P's a set. It's not a number.
Oh.
B minus A?
Just B minus A. Wonderful. If I add up that distance and that distance, when it's all said and done, I get the whole interval, which is B minus A. If I were to add up all those little intervals, the whole interval is B minus A. It's that distance. When you add up all those little partition intervals, the distance between them, you're left with B minus A, the distance of the whole interval. All we did was add up one little part at a time. We're just going to make the substitution a lot in our algebra from here on out, so I wanted to make it explicitly clear. Good? Okay. Our first term. So let f be a function on a closed bounded interval R. Bounded was there. If we find two numbers, m and big M, notice that they don't have their subscript, so they're not necessarily what we're talking over there. If we find two numbers, little m and big M, in R, such that little m is always less than or equal to what the function reaches on the whole interval, and big M is always greater than or equal to what the function reaches on the whole interval, then for any partition you pick, m times that distance is going to be less than or equal to any lower Darboux sum you pick, and the upper Darboux sum you pick is always going to be less than or equal to this area. Here's what I'm saying in picture. So we'll come back here. What is little m now? Not little m sub I, not this little m, but little m overall. It's the lowest value the function reaches on the whole interval. So in this case, it looks like it might be this value. So it's this value or less. Little m is a number less than or equal to what the function reaches on the whole interval. So little m might be this high. And notice that little m times b minus a then is the area of the rectangle we use with just that height. You see that?
Mm-hmm.
You wrote m sub I. Is it?
Sorry, thank you. Just m, not m sub I. And big M is greater than or equal to the value the function reaches anywhere on here. So big M might be this rectangle, or big M might be this point. And then m times b minus a gives you the area of this rectangle. So now notice what we're saying here. We're saying when you use little m times b minus a, that area is always less than or equal to the area a lower Darboux sum gives you. We're going to prove this, but make sure it makes intuitive sense. The area of this rectangle is always less than or equal to the area we got from all the lower rectangles here that we added up, the way my picture was first drawn.
What are we going to prove this for? Like, is this just for practice, or is it
No.
used?
No, it's very useful. It's a little lemma that we're going to use to prove one of the bigger ones. And then any upper Darboux sum we pick, so now that's all the upper Darboux sums, is always going to be less than or equal to big M times B minus A, that massive rectangle. Right? So that massive rectangle is a way over approximation for the area. That little rectangle was a way under approximation for the area. And the upper and lower Darboux sums are always going to be somewhere in between those two very crude approximations. Right? Okay. That's all we're saying here, and that's what we're going to prove. And we'll just prove one of them because the other proof is almost identical. I don't care which one we prove. Do you guys have a preference?
We could do both.
Guess we'll do this one. Proof. Little m times b minus a is less than or equal to the lower Darboux sum of f with some partition p. Now notice it's implied that f is a function from the closed interval a, b to r, and that p is some partition on f. Well, and p is some partition on that closed interval a, b. That's all implied in what I've said here. And b minus a, talking about the exact same partition. Good? Alright, the proof is basically just an algebra proof. What is the lower Darboux sum equal to? We won't bother with all the words, it's just the algebra here that's important. By definition, the lower Darboux sum, when you give it some function f and some partition p, is equal to the sum from I equals 1 to n of little m sub I times x sub I minus x sub I minus 1. Exactly what we wrote over here. Right? To observe, maybe make this one explicit, observe that n is less than or equal to m sub I for all I for 1 less than or equal to I less than or equal to n. Okay. In other words, all our minimum points on some interval, on some particular interval of our partition, has to be greater than or equal to a minimum on the entire function. By definition of little m. Is there anything confusing about that? Little m is the lowest point the function reaches on all of AB. Little m sub I is just the lowest point it reaches on this interval, and then this interval, and then this, and then this, and then this, etc. And so the lowest point it reaches on some particular interval can't be lower than the lowest point it reaches on the entire function.
I lost the definition somewhere in the word, so can little m be smaller?
Yeah, but the biggest it can be is the lowest point the function reaches.
Right, but just to clarify, it can be any point below that as well.
Yep.
Okay.
It's just some number with the property that it's less than the value of the function on every point. Where do we write that? Right here.
Okay. Fine.
So this is what we're proving. So let f be a function from AB to R such that it's bounded. Let m and n be real numbers such that this is always the case. And now we're proving then, for any partition P, this is the case. So notice we don't know anything about partition P, it's just some partition. We have no clue about it, we just know it is a partition. So, whatever our lower Darboux sum is, it's equal to this thing. Right? And we know that whatever little m is, it's always less than or equal to the lowest value the function achieves on some interval. Good? So now it's just algebra. Then, LFP, which is equal to the sum from I equals 1 to n of n sub I times x sub I minus x sub I minus 1, that is going to be greater than or equal to the sum from I equals 1 to n of m times x of I minus x of I minus 1. Right? If I take all my little m sub i's and I replace them with just little m's, then all I could have done was made the function smaller. I couldn't have made it bigger, based off of what we set up here. So then that, which is equal to, now notice I have m times something, and then m times something that I'm adding up. So I'm adding up a bunch of terms multiplied by m, so I can factor that m out of my sum. So that's the same thing as m times the sum from I equals 1 to n of x of I minus x of I minus 1. You follow that? Just factoring out the m from all those terms that we're adding up. Now, what is that sum? B minus A. If we add up the distance of all our little intervals, when it's all said and done, we got the whole interval. B minus A. If we add up all these little intervals, that's what our x of I minus x of I minus 1 is. That's the distance of some particular interval. If we add up the distance of all those intervals, when it's all said and done, we have this distance, which is B minus A. So that's m times B minus A, which is exactly what we were trying to show. Right? To show the uppercase, if we want to see it, it's almost just replacing our L's with U's and our less than or equals with greater than or equals. So this is big M sub I. Observe that big M is always greater than or equal to big M sub I. Right? The highest value the function achieves on the entire interval AB is always greater than or equal to the highest value achieves there, or there, or there, or there, or there, etc. So if that is the case, then our upper sum is equal to, replace this with big M sub I, which is less than or equal to, replace this with big M, which is equal to big M, which is equal to big N. Okay. There we prove both cases. Pretty straightforward. Nice simple algebra. Okay. Next, moving on to refinement of a partition. So given a partition P, another partition P star is called a refinement if it uses the exact same points as P and then just adds points on top of that. So let's draw a picture of a refinement and then we'll get into the definition. I think it will be very clear what we're saying. So we've got some closed interval A to B. We can create a partition on that interval. So we just pick some points to divide up the interval. We have to use A and B and then pick any points in between we want. So I pick this one, this one, this one, and this one. Okay. I just made a partition. We call this point x0, x1, x2, and x3. There's a partition, P. P is equal to the set of those points. Remember that a partition's a set. Alright, now we are creating a refinement on P called P star. How do we create a refinement? We take our initial partition and we just add more points. We divide this up into even more pieces. That's what a refinement is. So maybe I add 2 points there and then a point there. Okay, that's now a refinement of P. So we might use for this. So for our second one, we might call this point y0, y1, y2, y3, y4, y5, and y6. So now we created a refinement of our initial partition, which just divided up more, and now it's divided up into 6 parts. And so this partition now is y0, which is the exact same as x0. Keep track of that. Then we had y1, then we had y2, and then we had y3, which was the exact same point as x1. And then we had y4, which was the exact same point as x2. And then we had y5, and then we had y6, which was the exact same point as x3. So notice this is still a partition on AB. And notice it uses all the exact same points that P used. All the points in P show up somewhere in here. That's all refinement is. You divide up more using your exact same points. Yep, if you're shaking your head like, why are you explaining this much? You got it. Okay. So, now let's read the definition. Given a partition P, another partition P star is called a refinement of P, provided that P is a subset of P star. Notice this is a subset of this. Everything in here is also in here. Simple, right? Okay. Now here's some notation. It's really simple, but it can get confusing because of all the subscripts, so let's make sure it makes sense. If P star is a refinement of P, then for each interval in P, notice that the n refers to how many points are in P. If we're looking up here, our n is equal to 3, in the example I have drawn here. N is how many points, or is how many parts the partition P divided up into. It divided it into 3 parts. So, down here. If P star is a refinement of P equal to x naught to xn, then for each part, each partition interval in P, the partition points of P star in a particular interval define a partition, P sub I, on that interval. Okay, so let's make sense of this real quick. So we're saying with this that we should be able to define a P sub 1, a P sub 2, and a P sub 3. We're saying that for each I between 1 and n, we're going to define a partition P sub I, whose points are the partition of the ith interval of P. So in this case, P sub 1 is the interval points on the first partitioned interval x naught to x1. So notice we took this interval of our partition and we divided it up with our refinement into even more pieces, right? So P1 is the points y naught, y1, y2, and y3. These are the partition points of our first partition interval of our initial partition. Here's our partition P. Here's its first partition interval. Here is how the refinement partitioned up its first interval. Let's look at P2. P2 in this case is just y3 to y4. It didn't add any other points. That's how it partitioned up the second one. And let's look at P3. That's how it partitioned up the third one. And that was y4 to y5 to y6. You see it? All this is giving us, it's a really simple idea, but it's easy to get lost in notation, is if we have a refinement of a partition, that is like breaking our partition up into a bunch of sub-partitions. That's all we're going to be doing. So we're going to start out with some partition P, we're going to apply a refinement, and then we're going to look at each of its sub-partitions, or whatever you want to call those. So let's read the definition one more time, and I think, well, not a definition, but a note one more time, and I think it'll be perfectly clear. If P star is a refinement of P equal to x naught through xn, then for each I between 1 and n, the partition points of P star in that partition interval define a partition P sub I of the interval. Good? Clear? Alright, if that's clear, I think we're ready to move on now to what's next. And we'll move back over here, so actually I have space. We're only 40 minutes in. Good enough. Okay, all this is not us. you have any questions about anything we've covered so far?
Just to clarify, it looks like a partition, or a refinement of a partition can just be the partition itself, right?
The refinement of a partition is a partition, but we can also talk about the partitions it produces on the intervals of our initial partition, which is going to be a useful thing to talk about.
Okay.
So we did that, we did that. So now we're ready for the refinement one then. So, proof let f be a function a, b to r be bounded and let P be a partition of its domain A, B. If P is a refinement, if P star is a refinement, of P, comma, then we get two things. We get that the lower sum of f of P, lower Darboux sum, is going to be less than or equal to the sum we get when we use our refinement. And the upper sum with our refinement is less than or equal to the upper sum with our partition. Okay, so notice that when we use a refinement of a partition, we're going to get a better approximation of the area, right? So the lower sum can only get closer to the actual area, which we know is greater than the lower sum. And the upper sum can only get closer to the actual area, which we know is less than the upper sum, less than or equal to. So hopefully it makes intuitive sense what both these are saying, and we'll prove one. Doesn't matter which one. Is there one you want to see? All right. So, one. I don't know. We already said that. Let all of that, so we've already got that. Okay, so one. We'll prove this one. I need my P star. Let P star be a refinement. Let P star be a refinement of P. Okay. 2. Let P1, P2, ... Pn be the partitions of the partition intervals of P. Exactly what we were talking about over there. So here's our partition intervals that P star induces on P. With me so far? Okay. So then our lower Darboux sum what's the right way to say this? We need to pick one partition. How does he say that? For I, let m sub I be a partition. I just need to pick a partition. Let x sub I minus 1 to x sub I be some partition interval of P. observe that m sub I times x sub I minus up here, minus x sub I minus 1 is going to be less than or equal to the lower Darboux sum on that ith partition, on the ith partition of, oh, we need the function first, f and then p sub I. Okay, so notice what we're saying here. We're saying pick the ith partition interval of p, right? And notice that p star induces the p sub ith partition on that interval. So here's some interval of p. Then p sub I is going to be the partition p star induces on that interval. Because p star could have divided that interval even more, right? And p sub I is how it divided up that interval. So then this is the area on that lower interval, right? The minimum height it achieves on that interval times the width of that interval, which is going to be less than or equal to the lower Darboux sum when we use the partition induced by p star, right? Now we're looking at the function on one interval. It's like redoing exactly what we did now talking about one interval. Here's one interval. Here's x sub I minus 1. Here's x sub I. Here's the function on that interval. Let's make it more dramatic to help see it all. Here's the function on that interval. So we're taking one of these intervals right here, and we're zooming up on it. That's all we're doing. And let's say it looks like this. I'm intentionally making it pretty dramatic so that you can see what's going on. So then, little m sub I is the minimum height reached on this interval. It is, if we make our y-axis right here, little m sub I is that, right? And the area of the rectangle with little m sub I is this area. Now notice that p star could have added points to this. So p star might have come along and added some points in here. So now the lower Darboux sum of this interval using p star's points gives us this rectangle, this rectangle, this rectangle, this rectangle, this rectangle, and this rectangle. It's always going to be greater than or equal to the one that we already had. That's using what we just proved before, right? But now we're just looking at this interval rather than the whole interval AB.
You're talking about, so it's a specification if they're on 6.1?
Yep, we're using 6.1. We're just using it on a single interval now instead of the entire interval AB. Still the exact same thing. So you good with this to this? Okay, so now the whole thing comes together. Then our lower Darboux sum on F with P, which is equal to the sum from I equals 1 to n of all these things. That is going to be less than or equal to the sum from I equals 1 to n of the lower Darboux sum, where we use p sub I. Right?
The sum of the lower Darboux sum?
You were comfortable with what we had on this line, right?
Yeah.
This line was talking about a particular interval.
Oh, okay.
This is just saying, now add them all up. Since this is true for a particular interval, this is true when you add it up for
So
every interval.
That's the sum of the sum, right?
Yes.
Okay.
Yes, that's exactly what it is. So going from here to here, we're just adding up for all the intervals, but this is exactly what the lower Darboux sum using our partition is. We just add up one little part at a time. Do you see big picture what we did here? It's not that messy of a picture. Maybe it's worth just drawing out. We said, look, you start out with trying to figure out some area. And one way you might do it is create a partition. And we'll be really crude and just do two to make it obvious exactly what this theorem's saying. So here's my x's. And here's my partition P. And the lower Darboux sum on it gives me those rectangles, right? Here's x0, here's x1, here's x2. Now will come P star, we'll add some points. And now we'll calculate the lower Darboux sum with those points. Might be something like this. Something like that, right? Now obviously the blue is giving us a much better approximation than the pink. The blue is using our P star, and the pink is using just our initial partition P. So right here, what are we saying? We're saying look at a particular interval. Look at a particular interval. So since we only have 2 with our initial partition, it's saying look at this or this. So look at this, then obviously the lower Darboux sum that our partition induces on that, the blue rectangles on this interval, are going to be greater than or equal to just what our initial partition gave us on that interval. That's using the theorem we proved over there. So we use that theorem to say the blue is bigger than the pink here, and the blue is bigger than the pink here. Sum them all up, the blue is bigger than the pink on all of it. And what is it when we sum up all the blue on all of it? That's the lower Darboux sum that P star gives us. That's its definition. So the sum of all those lower Darboux sums on each of the intervals is the lower Darboux sum using all of P star. Like I said, simple idea, but log notation, easy to get lost. Make sense? Okay. So, that, I think, is the hardest theorem in this section. And if you wrap your head around that, I think the whole section will come together for you. So, let's see what comes next. Oh, come on. Oh, yeah. So we did that. Okay. Here's a cool little lemma. Proof. For any two partitions, we'll call them P1, P2. Then the lower Darboux sum of F some function from AB to R. Sorry, should have specified that. F is a function from AB to R where F is bounded. Okay.
Are these two partitions are not
In any way related.
refinements, right?
They're not refinements of each other. They're just two random partitions. Then the lower Darboux sum on one of the partitions is always less than or equal to the upper Darboux sum on the other partition. It is impossible for you to find two partitions such that the lower Darboux sum on one of them is greater than or equal to, well, is greater than the upper Darboux sum on the other one. Impossible. Doesn't matter what partition you pick. That's what we're proving. You with me so far? Okay. 1, here's how we improve this. Let P star equal P1 union P2. Notice now P star is a refinement of both of them. It has all the points this one has, and it has all the points this one has.
It's refinement of both of them, but not of each of them separately.
It's a refinement of each of them separately.
But what if P2?
Here is some set.
Okay.
Here is some set. Union them together and call it that. Now this is a subset of that, and this is a subset of that. This is a refinement of both of those.
Right.
So then using the previous theorem, then the lower Darboux sum of f on p sub 1 is going to be less than or equal to the lower Darboux sum on the refinement. That's using our previous theorem. Our refinement gives us a better approximation. It can only make our lower sum better. It can't make it worse. You with me? And by definition of a lower Darboux sum, it's always less than or equal to an upper Darboux sum on the same refinement. Right? And then, this is the counterpart to the other proof. On the other proof, we just proved this part, but the counterpart would have been proving that the upper Darboux sum is less than or equal to the upper Darboux sum of f on P2. If you take a refinement of a partition with an upper sum, it can only make it smaller, because it gets closer to the actual area. And so that's the whole proof. So this is always greater than or equal to this, is all we're trying to show. Make sense? Okay. So now we're ready for two definitions called the lower integral and the upper integral. You'll notice that that's exactly what this chapter is about. So the definition is the lower integral AB of f, and then to specify that it's the lower integral, do we put the line under the A or just down here? So it's not necessarily under the A, it's just under that integral symbol. The lower Darboux sum is defined to be this one is going to be the infimum of all our not the infimum, the supremum. This is going to be the supremum of all of our lower Darboux sums for all partitions P. Let's see if that's roughly how he says it. Yeah, for all partitions, for all P on AB, on the closed interval AB, obviously we're saying that f is a function from AB to R that's bounded. Okay, so the lower integral, we're defined to be the supremum, the least upper bound of all lower Darboux sums. So take every possible lower Darboux sum you could do on something, and now take the highest they can ever achieve, their least upper bound, their supremum, and that's what we call the lower integral. It's basically saying as good as possible a lower Darboux sum as you could get. The best possible approximation you can get with the lower Darboux sum. The supremum, the least upper bound of all lower Darboux sums.
Isn't that just the integral?
No, you'll see why. That the lower Darboux sum and the upper Darboux sum are not necessarily the same thing. We'll see a counterexample. But in most cases they are. The upper Darboux, or the upper integral of f is defined to be the infimum of all upper Darboux sums you can make on f with p for all partitions P on the closed interval AB. The least upper bound. Make sense so far what those are saying? Okay. So, and notice by definition, then, that the lower integral is always less than or equal to the upper integral. Oops. Right?
What does it mean to have the colon equal sign? So f.
Defined by. Maybe we'll prove this one actually to make sure that makes sense. So let's do a proof real quick. Proof, just a real small proof. Given some function f with all the conditions that it normally has, and given partitions, whatever, we want to prove that the lower integral is always less than or equal to the upper integral of f. Okay? So, observe that for any partition then we'll start by using this one. Doesn't matter which one we start with. We'll just start with this one. What is this? This is the supremum of all lower Darboux sums, right? It's the least upper bound of all lower Darboux sums. So observe that for any p, first off, our lower Darboux sum is going to be less than or equal to our upper Darboux sum. Now, by definition, the supremum is the least upper bound of all lower Darboux sums. This is an upper bound of a lower Darboux sum. This is the least upper bound of all lower Darboux sums. So this is some upper bound. So we have L, F, P is less than or equal to the lower integral a to b of f. And that has to be less than or equal to the upper Darboux sum. Since this is the least upper bound on these sums, and this is an upper bound on these sums, then this is always less than or equal to this. This is always an upper bound. This is the least upper bound. This has to always be less than or equal to this. You with me? So now, notice that our lower Darboux sum is a lower bound for our upper Darboux sum. By definition, this is the greatest lower bound. Here is a lower bound for our upper sums. This is the greatest lower bound. Therefore, we get that our lower integral is less than or equal to our upper integral. This is a lower bound for this. This is the greatest lower bound for this. Therefore, this is greater than or equal to that. That's not negative a. That's a lower sum. Make sense there? Quick little proof. Okay. Let's see how the camera's doing. It doesn't show me. Guess it dies when it dies.
I do have a charger.
Oh, you do?
You have an Apple phone, right?
Yes. That would be wonderful. Fantastic. Okay. Thank you. Alright, so next I think we're doing an example. Let's see. The function that okay. So now the author's doing really quick to help. You see it, we've already talked about this, but doing it with the constant function. Where did I put my blue marker? So, proof. If f from a, b to r is bounded,
Isn't it?
and we don't even need to say it's bounded.
Yeah, it is bounded always, right?
Yeah, and f of x is equal to c for some number c in R, then our lower integral is equal to our upper integral on f is equal to c times b minus a, which is exactly what we'd expect. I don't know how much this is worth writing out. Obviously, we calculate our lower Darboux sum for any partition is just C times B minus A, which is less than or equal to this, which is less than or equal to this, which is less than or equal to an upper Darboux sum, which is that exact same thing. I don't know. You want to see it written out? Okay, let's write it out. We don't bother with words. We can just see all the algebra. Maybe we'll say let P be any partition to start. Okay. Then C times B minus A is going to equal our sum from I equals 1 to n of C times B, not B now, but x of I minus x of I minus 1. You good with that? All I'm doing is, instead of doing B minus A, I'm rewriting it as a sum of all the partition intervals, which is equal to now the sum from I equals 1 to n of little m sub I times x of I minus x of I minus 1. Obviously, the lowest point that the function achieves on any interval is just going to be C because the function is always C. You good? And this is exactly what we mean by the lower Darboux sum of f with P, which we now know by definition is less than or equal to the supremum of our lower Darboux sums, so our lower integral from A to B of f, which we proved in our previous theorem is less than or equal to the upper integral of f, which we now know is less than or equal to the upper Darboux sum on it. By definition of this, the upper integral is the infimum of all upper Darboux sums. So that gives us this, which is equal to the sum from I equals 1 to n of big M sub I times x of I minus x of I minus 1. But M sub I is just C, and then C, multiply all those out. Maybe you're okay with me just going straight to C times B minus A. So we got C times B minus A is less than or equal to both those things, is less than or equal to C times B minus A. Therefore that equals that, and that equals that. Therefore those equal each other. Good? Okay. The function, that was constant, we already did that. I thought we had one more major theorem. Are we already done? We have one more example, and this is the very last example. Geez, I hope I didn't skip something. That seemed quicker than I thought it would be. Alright, and then the last example is to show you a case where the lower and upper sums, maybe I won't do this one for you, make you think about it and have you kind of answer questions for me as we go. So just think about this function. We won't really do a proof, we'll just say, consider, well, who cares? I don't need to write this out because we'll just have you look at the function. Ignore what's up there. Okay, so look at this function. F from A, B to R by f of x equal to, which one's 0, which one's 1? Oh, we're doing really concrete, okay. 0 to 1, and we do 0 for rational. So this function spits out 0 if x is rational, spits out 1 if x is not rational. Obviously all our real numbers can be split into the rationals and irrationals. Okay, so now think about this function. What does this function look like first of all? This function is a nightmare. I've got on the closed interval 0 to 1, and then here's 1 up here. So at 0, let's see, 0 the function is rational, so it's a 0. At 1, the function is rational, so it's a 0. But now in between, every time I come across a rational number, I put a 0. Also, every time I come across an irrational number, I put a 1. Now obviously if we graph these things, it's going to look like two vertical lines, but it's easier to help us think about it if we think about it with just the points. If I did all the points, they just look like vertical lines, but the point is just a bunch of points. Right? That's what this function does. For every point, if the point's rational, we assign it 0. If the point's irrational, we assign it 1. This function is going between 1s and 0s like crazy. It's a nightmare of a function. Now we're going to look at the integral of this function. Well, first off, maybe you can already just see it, and we don't need to get into too much details. Let's just see. Let's look at the lower integral from 0 to 1 of f. What's the lower integral going to be of this thing?
1.
The lower integral?
0.
0. It's going to be 0. How do I know that? I know that for any partition you choose. It does not matter how you choose to divide up 0 to 1. Doesn't matter how you choose to divide it up. The rationals are dense in R. Doesn't matter how small partition intervals you make. I am guaranteed that there is a rational number in there. What is little m sub I? So our lower Darboux sum of f with some partition P, no matter how perfect you make that partition, this is still equal to the sum from I equals 1 to n of little m sub I times x sub I minus x sub I minus 1. Right? Any lower Darboux sum you pick is of this form. M sub I, doesn't matter how small you make those partitions, is always going to be 0. We assign the number 0 if the number is rational. No matter how much I divide up this interval, no matter how small of a partition I make, since rationals are dense in R, I'm always guaranteed they contain a rational. Therefore, the least value that the function takes on any subinterval you choose is always going to be 0. So it's always going to be 0 times the distance, 0 times the distance. Add them all up, you're always going to get 0. Similarly, when you look at the upper Darboux sum, for any partition P,
Your partition points can all be irrational, right?
doesn't matter, because we're talking about the partition intervals. On the interval, it will still contain a rational number. But yeah, you can pick, well, no, they can't all be irrational because you have to start with 0 and you have to end with 1. All the other points in between can be irrational if you want. A partition has to start with A and it has to end with B. So if we're talking about a partition on 0, 1, our first point is always 0 and our last point is always 1.
But if all the points that aren't 0 or 1 are irrational,
If all the points at what?
that aren't 0 or 1
Are irrational.
then wouldn't the Darboux sum for each of those be up at 1?
Now,
I'm missing.
let's look at a really concrete example. That meets your condition. We'll have P equal to 0, 1 over 2 pi, there's an irrational, and 1.
Okay.
I can still find a rational number between 0 and 1 over 2 pi. Therefore, the minimum height that the function takes on this interval is still going to be 0. Look at the interval from 0 to 1 over 2 pi. What's the minimum height the function takes on that interval? 0. Now look at this interval. From 1 over 2 pi to 1, what's the minimum height the function takes on that interval? 0. What is confusing me?
The part that's confusing me is the interval part. Like, we're not.
M sub I is not necessarily the value at the edge of the intervals. It can be somewhere in between. So it happened to be the case with our picture a lot of the times that our M sub I was at one of these ends.
Okay.
So maybe that's what's throwing you off.
That's what it was.
Okay. Yeah, it's very possible that a particular interval, on that particular interval, the function looks like this.
Right.
And then our m sub I happens to be in the middle now.
So m sub I is always 0.
For this function, yes. Little m sub I is always 0.
Right.
Now, if we're looking at the upper Darboux sum, then big M sub I
It's always 1.
is always 1. Right? So its upper Darboux sum is going to be 1 times this total distance is 1 is 1. So this is always equal to 0, and the upper Darboux sum of f is going to equal 1. Those are two very different numbers. So here's a counterexample. It's a really weird function. Most of the times, most of the next functions that we're used to working with, the lower integral and the upper integral are going to give us the same value. But here's an example of a function where the lower integral and the upper integral are drastically different numbers. And in such cases, we say that the function isn't integrable.
So when the upper sum and the lower sum are not the same, the function isn't integrable.
Yeah. Here's what we're going to do in the next section. By the way, the next section is where we cover the Archimedean-Riemann theorem, which is the most basic theorem of talking about integrals. So if I had to read one section out of this chapter, it would be that section. But we're going to define now the integral from a to b of f. First off, it only exists when this number is equal to this number, and then we define it to be that number. So if some number a is equal to the lower integral is equal to the upper integral. So if both these give the same number, then we define the integral from a to b of f to be whatever that number is. And intuitively, it gives us the area under the curve, which is why I chose big A. So that's what we're going to be, that's going to be the first definition we see in the next section.
So if our areas that we're summing up get basically, you could say infinitely thin, can you think about area under a point the same way that you can think of the slope at a point?
Kind of.
So can you find like the area under one point?
Well, no, the same way that you don't really have the slope at one point. You have the slope in a limit where 2 points approach each other. And yes, the integral, we have adding up the area where the interval's distances approach 0. So here's a common way that we'll calculate an integral. So pick some function. F of x equal to something like x squared. Nice simple function to start out with. Shoot, we don't know how to. Let's keep the sums that we know how to do really quick. So f of x equal to x. Note that we remember that the sum from I equals 1 to n, or of I, is equal to what? N times n minus 1 over 2. Remember that? Okay, we're going to need to use this fact over here, so just want to remind you of it. And we're going to calculate this integral. So this integral, say f of x equals x. Now we want to calculate the integral on the interval a, b. Let's pick an interval. I don't care what interval we use. We'll just use 0, 1 to keep stuff really, really simple. Let's do 0 to 2. That way you might see a case that you didn't really expect. So we'll look at the integral from 0 to 2 of f of x. And we're going to put a little dx there. We'll come back and explain why we're putting that dx there in a little bit. In short, here's what we do. You know what? And we'll make this all make sense right now. There's no reason we can't. So let's graph our function. It's just f of x equals x. That's just a vertical. That's just a line like this, right? Mm-hmm. And this is a nice simple case. We're going to calculate the area from 0 to 2. That way we can actually check it with just our intuition. Nice simple case. So we're looking for the area of this triangle. And we already know it's half the base times the height, so that we know that the area is just going to be 2. We already intuitively know that, right? Here's what we're going to do. I'm going to take 0 to 2 and I'm going to divide it up into n pieces. And to keep things simple, I'm going to make each of the pieces I divide up to into the same size. So I'm going to divide it up into n equal sized pieces. So whatever we divide it up into, I divide it up into n equal sized pieces. And now, I'm going to create rectangles with those. Those are meant to be equal width rectangles. Forgive the picture, as it lies to you. And I may use a lower sum, doesn't matter. But I'm using the lower Darboux sum. Could have used the upper just as easily. Just pick one. And then our last rectangle doesn't have any height, right? So if I want to calculate the area using the rectangles I had here, that would be the sum from I equals 1 to n of f of my height. Let's see, what did I use for the height? Shoot, I used the left-hand point. Okay, notice that I equals 1 to n is going to be the same thing as the sum from... Pretend I use the right-hand point on all these. We did the upper Darboux sum. Makes the algebra a little bit easier so I don't have to mess with the sum. And the overall picture doesn't change anything, but just so I don't confuse you. So we use the upper rectangles, not the lower rectangles. You with me so far? So the height of each of these rectangles is just the height at the right-hand endpoint of the rectangle, right? So it's just f at the right-hand point. Now notice, what is this right-hand point in terms of n?
It's x sub n, 1.
It's I times n over 2.
Oh, in terms of n.
In terms of n and in terms of I. So we're going from I to n. Notice that when, 2 over n, not n over 2, sorry. 2 over n. Each of these are going to have length 2 over n, right?
How did we...
I divide this up into n pieces.
Okay.
So this is now divided up into n pieces. Should have said this first, sorry. Divide this up into n pieces. How big is one of these pieces now?
2 over.
2 over n. I took this thing, which is length 2, and divided it up into n pieces. If I divide it up into 2 pieces, then I have lengths 1, 2 over 2. If I divide this up into 10 pieces, then each of those lengths is 1/5. 2 divided by 10.
So why are you multiplying it by I?
Well, yeah, we'll get there. But make sure that this makes sense. The width of each of these now is just n over 2. You with me so far? Okay. So now, what is this point right here? It's 1 times 2 over n. What's this point? It's 2 times 2 over n. What's this point? It's 3 times 2 over n. It's 3 of these distances away. This is 4 of those distances away. 5, 6, 7, 8, 9, 10, all the way to n of those distances away. So that's what this point is. The right-hand point of each of these triangles, for the first one, is just 2 over n. For the second one, it's 2 times 2 over n. We're just counting how many distances we went to the right.
Okay.
So notice that f, plug in 1 to this function, 1 times 2 over n. That is the height at this point. That gives us that height, which is the height of my first triangle.
Right.
When you plug in 2 for I, then we're saying go 2 over n, go that distance twice, 2 over n's. So we go 1, 2 over n, 2 over n's, and get the height there. It's the height of my second rectangle. Is that making sense? Notice what's the height of my nth rectangle. Plug in n for this. N's cancel out, you just have f of 2. So my last rectangle, my nth rectangle, has the height that you get at 2. You plug in f of 2, what do you get? The height at 2. So this is just giving me my height of my rectangle for each of these rectangles. You with me so far? So I need to take the height of each of those rectangles and multiply it by their width. What's the width of each of the rectangles?
X sub I minus X sub I minus.
But they all have the exact same width in this case, so it's just
2 over n.
It's just 2 over n. Length times width. This is the height of the ith triangle. This is the width of the ith triangle. Notice all the triangles have the exact same width, so that's easy. The width is always 2 over n. It's the height that changes. The height is the value of the function here for the first rectangle. It's the value of the function here for the second rectangle. It's the value of the function here for the third rectangle. You see that? Good? this is exactly what you would calculate, this number is exactly what you would calculate if I told you to approximate the area of this triangle using these upper sums, dividing it into m pieces. If I chose n to be 5, you'd go through this exact process, plugging in 5 for n.
Okay.
Are we seeing it, or do we need to make it more explicit and do an example where we divide this into like 2 pieces?
Let's do it.
Divide it?
Sure.
Okay, so let's look at the special case where n is 2. If n is 2, that means I'm just dividing this into 2 pieces. So what's my approximation going to look like? Here's my triangle. My approximation rectangles are going to be this rectangle and this rectangle, right? That's dividing it into 2 pieces. So the width here is going to be 1, and the height here is going to be 1, and then the width here is going to be 1, and the height here is going to be 2, right? So when we add it up, we're getting 1 times 1 plus 2 times 1, which is exactly what this formula is going to give us. So we're looking at the sum from I equals 1 to 2 of f of I times 2 over 2, sorry, n is 2, times 2 over 2, which is equal to, plug in 1, is equal to f of, when we plug in 1 for I is 1, 1 times 2 over 2 is 1. What's the height of the function at 1? 1. Our function is f of x equals x. Remember, our function is, we didn't write it somewhere, our function is f of x is equal to x, right? So when I plug 1 into that function, I get f of, oh, we won't do that yet, we'll just say f of 1 so far, times 2 over n, or in our case is 1, plus, now we're doing f of, what do I get when I plug 2 into this thing? 2's go out, we get f of 2 times 1 again. Or in other words, we get 1 times 1 plus 2 times 1, or we get 3, which is exactly what that would have given us.
So where were we going with this?
Okay,
I forgot where we were going.
so that was calculating the area using 2 of these rectangles. This is, in general, calculating the area using n of the rectangles.
So do you, when you're calculating an integral, do you say from I to infinity?
Well, yeah, so now here's how we get the actual integral. We're going to now take the limit as n approaches infinity of this sum. And that's going to be our integral.
It seems awfully tricky to solve.
Yeah, it's not nearly as simple as derivatives are, but we can still solve this pretty easily. This one actually happens to not be that bad. This is equal to the limit as n approaches infinity of the sum. Well, let's not write the sum yet. Notice that n is a constant, so I can pull my n out, my 2 over n. So I can pull that out, right?
What's 2 over infinity?
Not out of the limit,
Yeah.
but out of the sum. We still have our limit there.
Okay.
Yep. Alright, so 2 over n, pulling that out, we still have the sum from I equals 1 to n. But what is f of I times 2 over n? It is just I times 2 over n. Remember what our function is. Our function is just f of x equals x. If our function was f of x equals x squared, I would have squared whatever was in there. But we want to keep it really, really simple so that we can use this sum. Okay. So, that's what equals. Notice now I have another 2 over n. I can pull that out again. And then I can evaluate the sum. So this is equal to the limit, as n approaches infinity, of pulling this one out now. We get 4 over n squared times the sum from I equals 1 to n of I. Right? That thing. Yep. So now this is equal to the limit as n approaches infinity, using this thing, of 4 over n squared times this thing, n times n minus 1, all over 2. We'll just come down here. With me so far on the algebra? Okay. Let's distribute that numerator. And now we're just calculating the limit, same way we've been calculating limits from the beginning of time. This is the limit as n approaches infinity of, let's see, we get n squared minus n all over, oh sorry, I've lost my 4. We get 4n squared, I'm going to completely distribute the numerator. 4n squared minus 4n all over 2n squared. With me so far? Okay. Now, I'm going to split this into two different limits. The limit of a difference is the difference of the limits. So I'm just going to split this into two limits. This is the limit as n approaches infinity of our first term, 4n squared over 2n squared, minus our limit of our second term. And now, hopefully, you can see what it's going to equal. 4n squared and 2n squared cancel out, leaving me with just 2. The limit as n approaches infinity of 2 is just 2. Right? The limit of a constant is just that. So when we evaluate this, we just get 2 minus, what's this limit? 0. N's cancel out, so we're left with 4 divided by 2n. As n approaches infinity, that just gets smaller and smaller and smaller and smaller and smaller. It goes to 0. So it equals 2. So the area of this triangle is 2, which we knew it was. And now you told me, now you know what I told you. Go back and make sure you understand our sigma formulas because you use them all the time in calculating integrals. Because an integral is just a sum of areas in a limit.
So you don't really take the infinite sum, you take the limit of the sum as n approaches infinity.
Say it however you want, it's just terminology. The exact thing we did is written right there. We calculate that limit. The same way that the integral, or the derivative was just a limit of the difference quotient, an integral is a limit of
Could you have written it
the
as
areas.
the sum from I equals 1 to infinity rather than with the limit as n approaches infinity?
Well, what does that notation mean? I mean, if you mean by the sum from I equals 1 to infinity,
Yeah.
is that, how would you define that? I mean, I would guess that you'd want to define that as a limit as n approaches infinity of the sum from I equals 1 to n. Define it in terms of limits we already know.
I was just wondering because that's how I've seen it in the past.
Oh, I would guess that that is what they meant by that. Sorry. Fine that way. Yeah, so that's how we're going to be calculating integrals. And you're going to have problems just like this on your test.
Okay.
Yeah. But that's just way ahead. So, that's it for material.